So in this video, we'll look at the way to find the area of certain region bounded by the polar curve r equals certain function in theta. And let's look at the current picture. Let's say you're given a polar function, and I give you the polar curve already. And in this picture, actually, I would like to find, for example, certain shaded area like this. And let's give some markings here. The fact is that let's assume that this line, the angle is the angle is theta naught. And let's say the angle up to this line is actually theta 1. And let's think about the area element in this case. The area element essentially means that you have to look at a very small part and we can try to do some approximation. For example, if you now take a very small part like this, and let's say the angle between this is extremely tiny, extremely small. So if you take out this part, let's think about it. You take out this part, and please think about the original area formula for certain region on a circle. If you recall what you know, back in the case of a circle, if you look at the area here, the fact is that we can use the formula 1 over 2 times r squared times theta, right? And theta now, of course, is in radian. It represents the angle here. And that's the way to find the area. If it is a circle, if this length is an arc in a circle, and approximately speaking, when the angle is so small, in this case, when the angle is so small, so approximately speaking, this length around here, you can really approximately think of it as an arc in a corresponding circle when the radius r is fixed, right? And it only happens when, of course, the difference of the theta naught and theta 1 is so small, and we can make such an approximation. But anyway, based on this fact, we understand that the area element can be think of because of this formula is half times r squared times the very tiny difference of the angle. I use delta theta to represent that. And it gives you a sense that in terms of the differential notation, we can use the every element half times r squared d theta. And okay, so I think it's a correct position where we can give you the area formula for the purple region here from the angle 0 naught to 0 1 like this, right? And I think we have to integrate from the starting angle theta naught up to theta 1. And we have to use this area element, which is half times r squared times the theta. And basically, that's the area formula to find the area of certain region bounded by the polar curve. And let's look at some examples now. So please look at the current picture I drew here. It is, let's say, for the polar function, r equals 3 times sine of 3 theta. And in this case, if I'm asking for the area of one loop, please look at my language. The fact is that all the loops are identical. Area of one loop means you can maybe just as an example, you can look at this loop as the shaded part. I would like to ask for the area of this loop. And please think about how you can sketch the curve. And that's why the understanding of how you sketch and trace this curve is important. Please try to do something. To understand how to draw this formula, we know that the formula is half times the integral of r squared d theta, but let's try to understand the angle here and the starting point on this loop. Basically, I think the point you can try to look at the angle theta equals 0, the r based on this function is 3 times sine 0, which is 0, which means that the starting point on this curve, this is the starting point. We can think of it like this. So we can use the starting angle as 0. And you see, when you sketch this curve, you're actually going along this way when the angle keeps increasing. And basically, you gradually come back to the origin again. So the angle theta 1 here should be the next time you get back to the origin. Please note that there are so many times you go back to origin. I don't care about the other times, the future times where you go back to the origin again. I would just like to look at the second time. Because if you look at the future where it goes back to origin again, it is not the loop we look at. Because this loop, I only want to look at it in the sense that you just go along this loop one time, right? And we have to solve this problem now. Get back to origin means r is 0. The r is the function at the top here, which means we can try to solve it now. We can try to make r equals 0, which means 3 times sine 3 theta is 0, which means sine of 3 theta is 0, right? And I understand that you can solve it. There are infinitely many solutions here because sine x equals 0 gives many solutions like x equals pi, 2 pi, and so on. So anyway, it means this angle, there are many solutions to make it 0. It can be 0, pi, 2 pi, etc. That's the behavior of the sine function because if you recall, the sine function is something like this, is pi, 2 pi, 3 pi, etc. That's the time you cut along the x-axis, right? So all of these give you infinitely many solutions. It means in terms of theta, there are infinitely many solutions also for the angles from zero, and we only care about the next time. As I emphasized, it goes back to the 0 again. So it means that the theta 1, based on what we learned here, should be the pi over 3 is the second time we go back to the 0. So it means that in terms of the area formula here, we need to write it here now, which is half times something, which is the integral of r squared d theta, and the angle is from 0 to pi over 3. And that's basically the area formula. And I trust that you're able to do this computation, but I can write the steps down for you. So basically, I wrote down all the steps here already for the area calculation of this loop. And basically, that's the end of this video.